So today we have the AND gate here, AND chip, and this is the AND HDL file, and this is the script. Now the script basically mentions the set of codes that have to be run in order to prove that this HDL file or this chip works. Now when we run it for the first time, only the first set, we will see that it ran this iteration compared to and.cmp, which imports the and.cmp file. That is a file for comparing, and this is what our output should look like. Right now our output is blank. So going back to the script, we'll see that first we will set the value of a to 0, b to 0, evaluate it, and then we'll give the output. Now our output is for 0 0 0, and the compare file for 0 0 is 0. So it's correct. Now I'm going to quickly run all of these together, where we'll set a to 0, b to 1, a to 1, b to 0, and a1 and a to 1 and b to 1, and evaluate each of these and give the output separately for each of these. And our output is for 0 1 0 1 0 0 and for 1 1 1. And comparing it, it's exactly the same. So the code we have written is completely correct, and the chip was tested successfully. Now let me run you through the code. So here we have first the NAND part, for which the inputs are A and B, and the output is the internal pin, that is NAND out. So let's say A is 1 and B is 0. So for 1 and 0, our NAND should be 1. Output of NAND should be 1. So NAND out is 1. And then NOT of NAND out will give the output, that is 0. So we'll see for 1 0 we have 0. Correct. Hence this was a AND gate. Out here we have the NAND 16 gate, which is nothing but the NAND gate for two 16-bit inputs that gives one 16-bit output. So we have the script here, the HTML file here, and let's just get our compare file. So when I compile the first set, the compare file gets loaded, and according to script, these will be the inputs to which these will be the outputs. Right now the output is 0. So now let me just run you through the code. For the first line, NAND of A equal to A of 0 and B equal to B of 0, these are the inputs, where A of 0 is nothing but the least significant bit of A, and B of 0 is the least significant bit of B. So let's say over here for A, the least significant bit is 0, and over here the least significant bit, that is B of 0, is 1. So similarly here, the output for this will be NAND AB0, and we again do NAND of NAND AB0 with both the inputs as NAND AB0 will give us the output, that is nothing but the NOT gate. So this NAND and this NOT gate make the AND gate. So let's run it, and this has been done for all the bits, 0 with 0, then 1 with 1. These are the positions from the rightmost side, from the least significant bit to the most significant bit, that is number 15. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, from right to left. So now let's compile it. When we compile the first set, for all 0 and all 0, our AND should be 0. Output all 0, and in the compare file all 0. I'm just gonna compile this entire thing. where each and every bit was run through the AND gate, and the output for each and every bit was given side by side, which form the entire 16-bit output. And our output file is completely same as the compare file, which states that the code written is correct, and hence the test of this chip was successful. Is AND 16-bit gate. We have the NOT gate, that is nothing but the NAND of the same inputs that will give the output of the same as NOT. So let's say A is 0. Let's say the input is 0. So A will be 0, B will be 0, and NAND of 0 0 is nothing but 1. So NOT of 0 is also 1. So let me just run the first set. So we will get the compare file. Okay, it should be this way: 0 1 and 1 0, and our output is 0 right now. So we are just going to compile this entire thing. Set in as 0, that is the input, and evaluate. Set input as 1 and then evaluate. So output is for 0 1 and for 1 0. So the code written is correct. Now we have the NOT 16 gate, which is nothing but the NOT gate for a 16-bit number. Now it is similar. It works just as the NOT gate, and the coding is very similar to AND 16 gate. Here, the NOT gate works as every bit of the input gets changed one by one from the least significant bit, rightmost bit 0, to the most significant bit, leftmost bit, 15th position. So let me just run the first set. So we will get the compare file. As you can see, for all zeros we get all ones, for all ones all zeros, and for 1 0 1 0 1 0 we get 0 1 0 1 0 1, and so on. So to check if our output matches the compare file, that our code is correct or not, let's run this entire thing. And we have the output exactly same to the compare file. Hence, the code written is absolutely correct. Let's take a look at this OR chip. Now, in this is the OR HDL file, and this is the OR script. So let's take a look at the HDL file. Now, to achieve OR gate, we are using NOT of both the inputs and feeding the NOT of both the inputs into a NAND gate, which is giving us the OR output. To achieve the NOT, we are using a NAND gate. Now, right now our output is blank. So running the first set, and this is the compare file. This is what our output should look like. So first set A to 0, B to 0, and so on. I'm going to compile it completely together, and we have the output as for 0 0 0 0 1 1 1 0 1 and 1 1 1. That is exactly similar to the same as the compare file. Hence the code written is correct. So this is the OR 16 gate. In this, two 16-bit inputs are passed, and the output is one 16-bit number. Now, in this, OR is performed for each and every bit. Now, for each and every bit in the first input, OR is performed for the corresponding position of the bits in the other input. For zeros, for 0 0 in the other, for the first portion in the other input. And we get the output for each and every bit. That is, we do OR 16 times. Now this is what our compare file output should look like. So going to run this entire thing. Now let's see, our output is exactly the same as the compare file, hence the code written is correct. Now we have the OR 8-way gate. In this we will be performing OR operation between 8 binary numbers of 1 bit each. So we will be first we will be performing OR operation between the 0th, 1th numbers, then second, third, then fourth, fifth, then sixth, seventh. So then we will left with 4 outputs, and OR operation between these 4 outputs will give another 2 outputs, and then OR operation between these 2 outputs will give us the final output result of all these 8 numbers. So this is what our output should look like. Right now there's nothing. So let me just compile this entire thing. See, like 0 0 0 0 0 OR operation between all these numbers one by one, all these numbers one by one, and we have the output that is exactly the same as the compare file. Hence the code written is absolutely. Here we have a mux chip. Now a mux chip is a multiplexer gate which has n selector lines, and for n selector lines we have 2 raised to n input lines. Now these combination of selector lines decides which input line's value is to be produced as the output. Now the input lines are numbered starts from the 0th position. So the first line is the 0th line, then comes the first line. So let's say the value of the selector line is 0, then the output will be the value stored in A, that is the 0th line. If it is 1, then the output stored in B will be the output. The value stored in B will be the output, which is the first line. So we have written the HDL file in NAND gates only. So let me load the compare file. The compare file has loaded. So as you can see in the compare file, for selector lines value 0, we have A as the output 0, again 0, it has 0, so 0 output. Then for again 0, it has 1 A, so 1 output. For 0 it is 1 A, so 1 output. Similarly, wherever there is 1, the value stored in B will be selected. 1 0, so 0 should be output 0. 1 1, so 1 should be output 1. 1 B, so 0 is stored in B, so 0 should be output 0. 1, but means V, so B, so value stored in B is 1, so 1 should be the output, 1 is the output. Now right now we have nothing in the output file. Let me just run the entire script, and let's check our output file, which is exactly the same as the compare file. Hence the code written is absolutely correct. So here we have the mux 16 chip. The mux 16 chip is nothing but exactly the same as the normal multiplexer gate, except for the fact that the values in the input lines will not be of 1 bit but will be of 16 bits, and the output will be of 16 bits as the value in the input lines, that is of 16 bits. So the code here written is, uh, instead of NAND we have used mux, since we have already written the code for the normal mux gate. So we can directly use mux here, and we have used mux for each and every bit, giving the output side by side for each and every bit, making it the entire 16 bit. So let me load the compare file. So as you can see, for selector line 1, the value in B is all zeros, and in A is 1 0 0 1 1 and so on. So the output will be all zeros, because the selection line is 1, and 1 for is the first line, which is nothing but B, and A is the 0th line. So let's check if the code written is correct or not. Let me run the entire script, and we'll see that this is the output, and it is exactly the same as the compare file, no change. Hence, the code written in the HDL file is absolutely correct. Here we have the MUX 4-way 16 chip, that is nothing but the multiplexer gate for 4 input lines with 16 bits of value in each of these input lines, and it has 2 selector lines. To satisfy the formula of n selector lines has 2 raised to n input lines, so 2 raised to 2, 4 input lines of 16 bits each. Now we will load the compare file. We have the compare file here. Output is nothing, so we are going to go ahead and run it, the entire file. So the output is going to be according to the selector line, one of the input lines, the value stored in one of the input lines. So there is some glitch in the application from the developers end, so we cannot view what's to the right side, the output, but it has an embedded code in it that compares the written code and the requirement of the code, and gives this end of script comparison ended successfully. Hence, the code written is. Here we have the MUX 8 by 16. This is exactly the same as MUX 4 by 16, except that there are 8 input lines and 3 selector lines to satisfy the formula, which I'm stating again. For n in selector lines, we have 2 raised to n input lines. So 2 raised to 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. So in MUX 4-way 16 chip, we used MUX 16 chip twice. First for the first two input lines and second for the last two input lines. Here for 8-way, we will use the MUX 4-way 16 for the first 4 input lines and then again for the last 4 input lines. And then finally MUX 16 to find the value of the first output here and the second output here. So let me load the compare file. Now, like I said, there's a glitch, but no problem. We have an embedded code in it that will state if the output and the comparison file are same. So just want to put it on fast and run the entire script. Here it shows end of script, comparison ended successfully, hence the code written is correct. That says that the output is exactly the same as in. Here we have a demux chip. A demux chip is a demultiplexer gate. Now a demultiplexer is exactly the opposite of a multiplexer. Here instead of 2 raised to n input lines, we have 2 raised to n output lines for n selector lines and only one input line. So a demultiplexer, the combination of the selection lines decides the value of the input is to be produced in which of the output line. So let's say, for example, our selector line's value is 0. So the output will be of the input value will be produced in the output of the 0th line, that is A. If the selector line's value is 1, then the output of the input value will be produced in the output line, first output line B. So to execute this demux chip, we will be using a set of NAND code, NAND commands. So let me just load the compare file. Remember, it was exactly in the opposite way of a multiplexer gate. So let's say our selector line is 1. So input is 1. So 1 means the first line after the 0th line. So that is B. B will get 1 and the value of the others will remain 0. So we'll run the entire code now and we'll see our output, which is exactly the same as the compare file. Hence, comparison ended successfully. Code written is completely correct. Here we have a DMUX 4-way chip. In this DMUX 4-way chip, we have a multiplexer gate which has 1, 2, 3, 4 output lines and has one input line and two selector lines for the formula n selector lines and 2 raised to n output lines. So we have already seen the working of a 4-way multiplexer and a DMUX chip. So it is combining those two. It's similar DMUX 4-way. So I'm just going to show you the compilation here if the code works or not. So load the file, compare file, and run the entire code. We have the output exactly the same as the compare file. So comparison ended successfully. Code written is absolutely. Now we have here is the DMUX 8-way chip, and to execute this, we will be using DMUX and DMUX 4-way commands. Since we have already done and worked them out in the past, so the working is exactly the same, except here we have 8 output lines and 3 selector lines. So 2 raised to 3, the formula for n selector lines 2 raised to n output lines. So 8 output lines and 1 input line. So we are just going to load the compare file and the output is exactly the same as the compare file as the code written is correct. Comparison ended success. So now we have the XOR chip. Let me explain the XOR gate to you. Its truth table is such that for both low inputs or both high inputs we have low output, and for exactly one input and one high input and the other uh, input being exactly low input, we have high output. So explaining it in further little more detail, as you can see here, let's say let's take the case 1 and 1. So we will pass it through a set of NOT gates and AND gates and finally OR gate. So for the top AND gate, we have 1 and not of 1. So 1 and 0, output is 0. For the bottom AND gate, it will be the same. Not of 1, 0 and 1, 1 and 0, 0. So both 0 or 0 becomes 0. So we have implemented it using a set of NAND gates, and we are just going to see the compare, check out the compare file. This is exactly the truth table. This is what our output should look like. So to evaluate this entire thing, and output is the same as the compare file. Comparison ended successfully, hence the code written is absolutely correct. Now here we have the ALU chip, that is the arithmetic logical unit. Now let me explain what the arithmetic logical unit does. Here we have two 16-bit inputs and 1, 2, 3, 4, 5, 6 1-bit inputs, one 16-bit output, that will be the operation performed between these two 16-bit inputs and two 1-bit outputs. Now, let's say I feed two 16-bit inputs into this ALU chip. So, depending on the value of these inputs, we will get the output. And depending on this 16-bit output, we will get the outputs of these two 1 bits. Now, let's say the value of zx is 1, then it will change the value of x to 0. The value of zx 1 sets x equal to 0. If the value of zy is 1, it will set the value in y to 0. And if the value in these are zeros, then it will not change the value of x and y at all. Now, if the value of nx is 1, then it performs a bitwise NOT operation and gives the 1 complement of x. Similarly, for ny is 1, it will perform the bitwise NOT operation for y and give the 1's complement for y. Now, if it is 0, then again x and y will go unchanged. Now, if the value of f is 1, then it performs addition function between these two 16-bit inputs. Not exactly the ones which were fed into the system, but after they have passed to zx, nx, zy, and ny. Now, if the value of f is 0, then it will perform the bitwise AND operation between the results of x and y that have passed to zx, nx, zy, and ny. Now the result produced by f, when it passes through NO, and if the value of NO is 1, then it will again perform bitwise NOT operation of the result produced by f, and if it is 0, then it will again go through NO unchanged, and that will be the final 16-bit result. That will be the output. Now the value of ZR and NG will depend on this output. Now if the 16-bit number is 0, then the value of ZR will become 1, or else it will remain 0. Now if the value of this 16-bit in decimal is negative, then NG will become 1 or it will remain 0. Now the code has been written in mux uh, in mux 16 gates, not 16s, mux 16, add 16, and 16, and so on. So we have performed all these operations in the past, and it is very easy to write these codes and implement them after understanding this chip. Now let me show you the working of the code. We have loaded the script. Let's load a compare file. It's, as you can see, really lengthy. So I'm just going to fast forward it so we can compile this quickly. And we have the output that is exactly the same as the compare file. Hence the code written is absolutely correct. Comparison ended successfully. So here we have a half adder chip. Now let me explain to you what half adder does. It takes two inputs and gives two outputs. One of the output is called sum and the other output is called carry. Now sum is calculated by nothing but the XOR gate. Sum is the XOR function between A and B, and carry is the AND function between A and B. So as you can see, the XOR of 0 0 will be 0, and AND of 0 0 will be 0. XOR of 0 1 will be 1, and AND will be 0. For 1 0, XOR will be 1, and AND will be 0. For 1 1, XOR will be 0, and for AND it will be 1. So let me just run this entire code. And as you can see, this is the compare file. It's exactly the same as our output. Hence, the code written is. Now we have the full adder circuit. Let me explain full adder to you. It is nothing but, if you look at the circuit, it is almost exactly twice of half adder. In half adder, for sum, we took the XOR gate, and for carry out, we took the AND gate. Now in full adder, we will be taking three inputs A, B and carry in, and two outputs sum out and carry out. Now sum out will be the XOR of AB and the XOR of AB and carry in. And for the carry out part, it will be the AND of AB. Then we will take the AND of carry in and XOR of AB, and we will take the OR of these two ANDs. So how we type the half adder code? Similarly, we have used simply these gates to type the full adder code. I'm just going to go ahead and compile the script, so we will know if the code written is correct or not. And it was able to run all of these lines, so the code must be correct. We'll check it just to be sure. This is the compare file, which is exactly the same as the output file, as the code written is correct. Here we have the add16 chip. Add16 is a chip that adds two 16-bit inputs and gives one 16-bit output. This addition is simply binary addition. To perform this, we will be using half and full adder chips, full adder gates. So let me explain this to you. It will do bitwise binary addition. So if first I'll be taking the half adder to find the sum and carry. The sum will be sum 0, output of the least significant bit 0, and the carry will be transferred to the full adder C input, and for that also we will find the sum of the next bit, and the carry found will be again transferred to the next full adder, and so on. We will have uh, 15 minus 1, 14 full adders, and only the first one will be the half adder. Now let me just compile this script, and it ran, so it must be correct. The compare file is exactly the same as the output file. And do note that with the last one, in which we get the carry, we are simply going to ignore it because this holds no value. We will ignore the carry bit of the most significant. Here we have the Inc16 chip. This is an incremental chip that increments the value of a 16-bit input by one, exactly one, that is a one, that is of 1 bit. Now for the code part, we can simply use an add 16 gate, where we will take the 16-bit input, and the output will be a 16 bits. Along with the 16-bit input, we will take another input B, that will be the value, another 16-bit input B, whose value will be false, meaning all will be 0 0 0 0 0, and we will make the value of the least significant bit of this B true, that is, it will become 1, and hence the output will be this plus this will give the output, that is incrementing it by 1. So let me just load the compare file so I can explain it better. So if the input is 0 0 0 0, if you add 1 of 1 bit, you will get 1 and the least significant bit. If all are 1, then when you add due to carry, all will become 0, and the carry bit of the most significant bit will be ignored, just like it was ignored in the add 16 chip. Now that I have explained it, let me compile this entire file. We'll see that our output file is the same as a compare file, hence the code written